Thank you. Thank you so much. Uh, so, yeah, I mean, I wasn't expecting a full house, uh, given the topic and timing both. And it's funny because I'm the one who put the schedule together and put myself at 3:30 slot. But yeah, I mean, see, the idea of this talk, what I want to do is provide some basic overview of for someone who might be starting to hack Postgres or wanting to hack Postgres and doesn't know where to start, what to do. I think the struggle that probably initially we had when we started hacking Postgres, and lot of time it was just going through the source code and figuring out things that probably already exist, things that we need to probably build. And I thought maybe giving a top-down overview of things might help others. So that's the sort of intent of this talk. So why hack on Postgres? And I think a few reasons why I think or I like hacking Postgres is that at least growing up when I was in college or when I was doing my master's, database systems was one of the things that was taught quite heavily in colleges, at least in my college where I graduated. And to be able to see that into actual production quality system database was a great thing. And a lot of things that we learn as part of, say, computer science program, they were actually, you can actually see them in action when you work on something like Postgres. It's also a very highly extensible database. What that means is it's not necessary for you to know the entire Postgres architecture or every bit and piece of code to be able to actually start contributing. There are enough ways by which you can know only a few things and actually start seeing some real impact of your work. The source code is extremely rich and good. It's well documented, well commented. So by just looking at source code, you can learn a lot of things. You don't really need to have, I know there are books that are out there on hacking Postgres, but you really don't need to know any of that. Just knowing the source code is good enough. It's a BSD license code, which means it gives you a lot of flexibility in terms of what you want to do with any change that you are making. You don't need to really worry about any of the proprietary stuff and whether if I do this change or if I try to build a product on this, would someone come after me? Definitely not. There are enough companies out here who have made their fortunes on Postgres. And finally, you just can become a better programmer. So even if you know programming, even if you know all of the bits and pieces, just looking at the code or following other hackers can make you a better programmer over a period of time. What skills do I need? You'd probably need to understand algorithms and data structures. That's the core of any bit of software that you write. If you know system programming, that's great, but I don't think that's like really essential. If you know C, your life would be easier, but these days there are a lot of extensions which are written in Rust and other programming languages, so it's not as if you don't know C, you can't do anything. There are probably plenty of opportunities. If you know C, obviously it's better because you can then look at a larger variety of code. And finally, you need to have aptitude to learn new things. You need to know how to use right editors and right tools, right plugins. I have seen people, even like Postgres hackers, using text editors and still doing pretty good, but I don't think that's the most productive thing. So knowing a bit of like hacks, how to use the proper editor is great. So having said that, let me say a few words. What I want to do is just explain the Postgres architecture at a very high level. Now obviously 40 minutes is not going to be enough to talk about even one subsystem of Postgres. Like there was a 45-minute talk just on, buffer cache management. So I won't be able to do justice to any of one subsystem, but I want to give you a top-down sort of view of different subsystems in Postgres, how they interact. If you want to learn more about a particular subsystem, where to look into the code for that. So this is a very high-level Postgres architecture. I borrowed this image from Wikimedia. So yeah, I mean, when I put together this presentation, there was absolutely no single image in the entire slide deck, and my daughters were like, that's not how you make presentation. So I said, okay, let me add one. So this is what I added. So Postgres is primarily a client-server architecture. That there are client-side applications like PSQL, which is a client to connect to Postgres database, is also an application which internally makes use of various client tools, libraries that Postgres provides to connect to the database, talk to the database, obtain query results and things like that. Obviously, you can have JDBC, ODBC, other connectors. So there are a whole lot of things that can go on the client side. The bigger chunk is server side, and that's what we will talk about in this presentation. So I like this image particularly because it sort of segregated the backend side of Postgres server nicely. So at the bottom level, you have your files. Postgres still doesn't work on raw devices. So what it works on is based, on top of a file system. So every object in database is represented by some kind of a file, and so it could be index, it could be heap, it could be even snapshots that you are taking, or transaction status that you are recording. Everything is a file. So that's at the bottom layer. Then there are bunch of processes that run. So Postgres is primarily a multi-process architecture. You have a lot of system processes that run, which are responsible for various activities. Like in the previous talk, there was talk about buffer eviction and how the background writer process is responsible for writing out buffer cache to the disk, so that when there is a need for a free space in the buffer cache, you can quickly replace it. Then there are auto vacuum worker processes whose job is to primarily make sure that your garbage in the database is cleaned up, and there are a bunch of other processes, and this might even be sort of a obsolete image, and there are more processes that get added with every Postgres release. Like you might have a wall sender which is doing physical replication as well as logical replication, and all sort of things. And at the top you have the backends which are responsible for communicating directly with the client applications or connections. So for every connection that is made into Postgres, a new backend process is forked, and the entire sort of life cycle of that connection is managed by that particular backend process. So yeah, I mean that's the basic architecture of Postgres. So as a developer, say if you want to start hacking Postgres, the first thing that you need to do is you need to get the source code of Postgres, because you won't be installing packages and working on things which are pre-packaged. That won't provide you enough flexibility. That's good enough to obviously run your applications, your SQL queries, if you want to see how queries are planned and how they are executed. But if you want to hack Postgres, if you want to change something in Postgres, you'll have to prepare to build Postgres from sources. And luckily that's very easy. I mean you can obtain Postgres sources in a variety of ways. You can download a tarball, but my favorite, and I think pretty much for any developer, would be to obtain via Git, because that gives you a lot more control. If you make change, you can track those changes, you can store those changes, you can work with multiple versions of Postgres within a single working environment. You don't really need to have 10 tarballs downloaded for 10 different types of versions that you are interested in. Postgres, I have listed down a few basic tools that you would probably need to build Postgres. And some of these are easily installable via, say, if you are on a Debian machine, you can do build essential, or on CentOS you can do development tools as a single command, and it would basically get you everything that is required for building any application, but Postgres in particular here. So yeah, you obtain, you basically install these development tools, and then you are ready. This is not presentation on Git. It can be a talk in itself, but these are some of the useful commands that you would probably find helpful when you are working with Postgres. Git fetch, and when you want to obtain new changes from the upstream repository, or if git checkout to create a new branch for your own work, or because you want to instead of Postgres master, you are interested in working on, say, release 17 version of Postgres. It could be for your work reason, or because that's where your interest is, and you don't really want to look into a branch which is under active development, and where your change can break something, but so can something else that's being developed, right? And then there are a bunch of commands. I would suggest probably you can look into Git manual to work through this. One of my favorite command is git work tree, and this I discovered quite lately, but I absolutely love it, because as a developer I need to work on, and our product, the product that I work on, Postgres Distributed, we have to support it starting from release 11 to now release 18 of Postgres. So you can imagine there are 8 major versions that we are working on at different points, and Postgres Distributed itself has its own a matrix of versions, and it was getting absolutely impossible to keep track of various environments where I have, say, a Postgres 11 build ready or Postgres 15 build ready. So Worktree gives you a very nice way by which you can create these, let's say, call them sub-environments within your main Git workflow, and then you can work on each of these work trees separately. So if you haven't explored Worktree, I would suggest do look into it. So once you have the source code downloaded, or either via Git or Tarball, this is the source code layout that you would see. At the top level, you have these various directories. As developers, I think our interest would typically be in the src directory or the contrib subdirectory that's there at the top level. And by that name, you would imagine that src includes most of the code that is required for Postgres to function, whereas contrib is nowadays it's known as extensions. All of the built-in extensions are in contrib module. So if you want to look at, so let's say you want to build a new extension and you want to see what already exists in Postgres. Am I redoing something, or can I get inspired by some existing work? So contrib is a good directory to look at. If you drill down into sources or src directory, I have made some subdirectories into bold because again these are probably the areas where you want to look into more detail. So backend is actually the entire server backend. Like we saw client server architecture, the entire server part is actually or most of it is under backend. The bin directory is where all of your Postgres binaries exist. So you can have initdb or pg base backup or pg receive log or pg bench. All of these are put under bin for the right reason. From that's where all the binaries are built. So if you want to look into any of those commands that come with Postgres and how they are implemented, that's the place for you to look into. Include is obviously, if you know C, these are all include direct files. Obviously there is a structure underneath that as well, but all of your header files are under include subdirectory, and that's a good place to start looking at if you want to see if there are any APIs that Postgres already provides. Let's say you are writing an extension and you want to know, is there a function call already to know if let's say status of this transaction is committed or aborted. You don't want to sort of rebuild the entire thing. So that's a good place to start. If in one of the header files, do I see something which seem related to what I'm looking at. Test directory is where all your test code exists, whether it's regression test or isolation test or tap test. I'm not going to get into details, but yeah, regression test is something at the very least you want to look at if you are hacking Postgres. Isolation tests are more suited when you are making changes to transaction management and want to see if any of my change, can it break any of the serializable properties, or if you want to test your code against those properties, isolation test is something that you would want to look at. But regression test is at least something basic that you want to see. Interfaces directory is all about your libpq interface, or anything that needs to talk to client is under interfaces. A little bit drill down under backend, and that's where most of these subcomponents that we want to look at are located in. There is a entire thing for about parsing. So when the query comes into Postgres, how do you parse, how do you plan, how do you execute? So those names are pretty self-explanatory, and that's where the code exists for each of these sort of steps in query execution. Contrib is interesting because it's quite likely that many of you would probably start with extension, and there are bunch of extensions out there. Even some of the very complex products built on Postgres today, they are built as extensions. And if you want to see how to write a new extension, looking at one of the existing extension is probably the best way to forward. Okay, so that's the source code layout. Now the next step is to prepare your build your Postgres server, and the first step is you want to configure. And this is a pretty AutoTools is a very well-known sort of tool in Linux and other Unix related subsystems. So you want to these days Postgres also provides Mason. I personally have never used it. It's sort of running in parallel with configure. Maybe over a period of time Mason would replace configure in Postgres too, but I still use configure as the basic thing. And some of these are obviously configure provides you n number of options. You can tweak things at the configure time, but for starters I think this is what you want to do. You want to turn debugging on. So enable debug, enable depend, which makes sure that your source code can be rebuilt fast, because it tracks all the dependency and everything. Tap test, something you want to run. CAssert is Postgres code is full of assertions. That means that the code is actively checking that certain conditions to be true or false at different places. But checking these conditions is quite performance. They can have performance impact. So they are not enabled by default. But as a developer, you want to enable CAsserts, because if you make a mistake, it can be caught quite early during the development cycle itself and not in the production environment. -O2, the C flags is something I do all the time. This gives you a lot better debugger symbols. You are turning off optimization so that if there is a code dump or if you are attaching to a process, you can see the stack trace quite clearly. And install is prefix is something as a developer, because if I show you my environment, you would see there are 20 different install directories that are already there, because I'm constantly switching between versions and Postgres flavors. So I can't afford to spend even like a 30-second or a minute to rebuild my environment. So they all exist all the time. I just switch between environments. So yeah, I mean, once you configure your code, you run make, and typically again there are like probably 20 different build targets or make targets that make supports. But most likely this is what you would do. You will do a make to build your entire source tree, or you can do make -c contrib. Minus capital C is obviously an option to a make where you are switching into subdirectory and building under that subdirectory. So Postgres by default won't build the contrib modules, but if you want, you can do make capital C contrib, which will build the entire contrib modules. Or you can do make world, which is obviously it's like building everything under the source tree. I think including docs. I'm not sure, but probably it also builds docs. And make install is like once you build, your binaries are ready, your shared libraries are ready. To put them into your installation path, you do make install. And the third thing is, to know whether you have installed things properly, nothing is broken, you typically want to run some tests. So make check would run the regression tests, which are the basic regression test in Postgres. They are pretty fast, they would probably be over in like less than a minute. But if you want to be more sort of, because the change that you are making is touching upon things like in transaction management area, maybe you want to run isolation test, or you want to run check proof, which is the type test framework that Postgres uses for things that regression test cannot really work on. Like you want to start, let's say you want to test PG based backup. Now regression test won't test that, but the type test can test that because it can start a server, it can start a PG based backup command, take a replica, start the replica, do all of those operations which are not possible under regression framework. So once your setup is ready, you are done, you would want to start the Postgres server. And yeah, I mean, typically as a developer, I use PGCTL all the time to start my server, and not any of the system tools. So let's look at the postmaster lifecycle, which is the main process of Postgres, right? When you start the Postgres server, postmaster process is what starts, and this is the main process, but at the same time it does very little things, few things, and that is by design, because you don't want postmaster to crash, or because if the postmaster crashes, there is nothing to sort of restart postmaster. So postmaster, even though it's the main process, it does little things. It will only monitor the system, the background worker processes, restart those processes if they die for whatever reason. If there is an error in auto vacuum daemon, postmaster would make sure that the daemon is restarted. It will also make sure that any user backend that is required to process client connections are started by postmaster. And in the bold, I have specified the actual file where you would see most of the code related to this. Now, obviously, it's not as if everything is there, but that's a good starting point. And my sort of purpose of this talk was to give those pointers that if you want to see where the postmaster code lies, so it's under postmaster.c under src backend postmaster. Or if you want to know what happens when the Postgres starts, how does it perform the wall recovery, how does it make sure that the database has come to a consistent state, that is under startup.c. So yeah, I mean, you can explore, read through some of these code in more detail. So that was postmaster, but to handle any user connection, or even the background worker processes in Postgres, we call them backends. So backend has its own life cycle in Postgres, and unlike postmaster, which should never die, backends can come and go. I mean, when a user connects, a new backend is forked, and when the client is done with its query processing, or it's exiting the PSQL connection, the backend also exits with it. So So backend has this kind of a life cycle where it would all the authentication work is handed over to the backend. So postmaster would force the backend and then let the backend do pretty much everything else that is required. This is how a query lifecycle looks like. So when a query hits database, we start with parsing, which is like tokenizing the query string into different tokens. Then you start analyzing those tokens. If I'm saying insert into something, that something has to be a table. It can't be garbage. And the analyzing stage of query processing actually looks after that. Once you have made sure that everything, all the tokens are sane, then you want to start planning for the query execution. The entire planning code is under SRC backend optimizer path. That's where various different paths for possible paths for query execution are generated. And then finally it comes to the optimizer to actually select the best path that is, let's say, planner things that it should use to execute the query. And then obviously, after that you hand over to the executor to actually execute the query. Okay, so we have parsed the query, we have planned it, we have given it to the executor to run. The next stage is, like in any query execution, you would want to access data. It could be user data, it could be catalogs, which are pretty much stored in very similar format. I mean, as far as Postgres is concerned, okay, we make some special handling or exceptions, but otherwise the format, the way the data is stored, the way the indexes are built, they are pretty much same whether it's user data or system catalogs. And all of that code of accessing either user data or system data is under SRC backend access. And you'll see a bunch of, I think I probably have a couple of slides on that, or maybe not. So you'll see ways to either do a sequential scan is under that subdirectory. If you want to use a B-tree index to access the data, it's there. If you are going to do some kind of a hashing to sort of satisfy multiple conditions and use multiple hash tables to do the filtering, it's there. So all of the code related to accessing data is under SRC backend access. Then comes transaction management, which is obviously a important part of any database system, and you need various things for transaction management. You need to establish transaction boundaries. We support sub-transactions, which means you have support for rolling back or committing sub-transactions. You need to track status of transactions. All of that code is under SRC backend access trans-AM. That's the primary place for transaction management. Even the wall recovery part, because I mean Xlog is sort of related to transaction management as well, because if you look at the ACID properties, the durability part is actually guaranteed by the write ahead logs. So even that part is under trans-AM. Buffer management. So SRC backend storage buffer is the place where all of the code related to buffer management exists. And those who were part of the previous talk, so that part of the code is under this subdirectory. And it obviously shared buffers is carved out of a larger shared memory pool that Postgres uses. And like I said, it's a multi-process architecture, which means you need shared memory for different processes to talk to each other, access data, because you don't really want one process to modify something and other process to not know about it. Most often you want to, obviously there are things that you don't want other process to know about, but when you are modifying some common data, you want all of them to know those changes. So that part is all handled by the buffer manager of Postgres. And if you are interested in, if you are looking for some performance issue in, certain queries are running slow because it's doing it's not loading my buffers correctly, or there are a lot of evictions happening. You have some smart ideas about how to improve the clock sweep algorithm. This is the place where you want to look at. The bottom tier of the architecture slide that we looked at was about all files, and that entire thing is handled by SRC backend storage file. And it could be that in Postgres nowadays there is a concept of shared file sets and things like that. All of those are handled or basically tracked under SRC backend storage. In Postgres, like I said, everything is filed. The max size can be 1 GB. That's where maybe it has some historical context, because in the older days, file systems wouldn't provide, like support files which are more than 1 GB. But Postgres as a database doesn't have those kind of limitations. So we sort of work around that by having multiple 1 GB files that can be mapped to a single table or an index or whatever object that you are looking at. SRC backend storage file is also, because like I said, there are a lot of performance optimizations that you need to do when you have hundreds of processes running, each trying to open the same file or trying to work on something. You have to coordinate all those accesses, and all of those things are handled here. Okay, so in the architecture diagram at the top tier, maybe I didn't talk about it, but there was a memory management thing, and memory is divided into two parts primarily. One is shared memory, which is where multiple processes are trying to access the same data. But there is also private memory that each backend needs to work on, right? It might be doing a sort operation or doing a sort merge, and it needs memory. So, or even for normal operation, right? You are building a parse tree or executing a query. So the private memory management of each backend is handled by Postgres' memory management module, and it's very powerful. I mean, those who know C would know that it doesn't provide you any guarantees around memory leaks. So if you palloc some memory and forget to free that memory, it will cause a memory leak, and that memory is and if you lose pointer to that memory, that thing is gone. I mean, there is no way for you to recover that memory in a C program. But what Postgres does is it provides you a nice wrapper around the libc heap memory allocation, so that you can allocate memory in different sort of contexts. Some of these contexts are short-lived contexts. Some of these are like long-lived contexts. And depending on your need, you can allocate memory in these contexts. It's a hierarchical sort of a memory management. So at the top, So at the top you have a top memory context where so a memory allocated in top memory context is never going to go away. So you have to be extremely careful. This is like a palloc in C. So if you allocate something here, it's not going to go away unless you explicitly free that memory. But something like a transaction context is only going to live till the transaction is active. So once the transaction commits or aborts, the transaction context would automatically go away, which means that if there is any memory allocation that that I won't care once the transaction is over, this is the right place to allocate that. But obviously, there can be even sort of finer tuned memory contexts. But let's for a moment think about this like this, that anything that doesn't need to survive after a transaction commits or abort can go in transaction context, and then you don't need to worry too much about memory allocated in that context, because Postgres would automatically make sure that that context is sort of deleted when the transaction ends. Cache memory context, on the other hand, it's like a cache of various things that Postgres maintains for performance reasons, and that will stay forever. So you have to be, just like top memory context, you have to be careful about cache memory context, but most likely you won't need to touch that unless you are adding a new catalog or something like that. Then there is lock manager in Postgres, and pretty much there are 3 different kinds of levels at which locking works in Postgres. At the top level, there is what we call LMGR or heavyweight locks. These are the logs that get acquired when you open a table, or if you are doing let's say vacuum full on a table, and you must have seen that access exclusive lock is getting acquired on a table. These are heavyweight logs, and Postgres has a built-in mechanism to find deadlocks within this layer of logs. So if there is a deadlock between multiple processes, Postgres would detect and sort of abort one or more processes. These logs you can hold for a very long time. Typically, Postgres actually doesn't release logs until the transaction is complete, and that's perfectly fine. There is no sort of hard requirement that how long these logs can be held. They can be transaction level logs, they can be session level logs. So and you have a complete what I would say granularity of logs that you can. I think there are 8 or 9 different levels of logs that you can acquire in heavyweight locking. The second is LW logs. These are not as cheap as heavyweight logs, and you are not supposed to hold them very long. You can't detect deadlocks if there is one which involves LW lock, so you have to be careful with acquiring and releasing these logs. These are like mutexes in Unix systems, and at the most basic logs are spin logs, and you don't even have a mode. You can't say that I want to acquire a spin log for reading or writing. Spin log is spin log. Once one process gets a spin log, no other process is gonna get a spin log. What's more important is that you are not supposed to put this process to sleep while holding a spin log. So you can't do any IO. You are not supposed to even do elog messages while you are like holding the log. So these logs are extremely short duration. Just for few instructions, CPU instructions, you can hold this log. And again, a lot of this code is under SRC backend storage. LMGR is where the heavyweight locking is. LMGR LW log.c these are mutex logs, and s_log.c is the spin log implementation. Postgres maintains a bunch of system caches, like we talked about cache memory, because if you are writing a program or you are making a change, often you would want to like open the table, or you want to know if if does a namespace with this name exist, or what are the partitions for this given table. All of those routines are implemented and are readily available to you in form of system caches. And I would suggest that before you look at anywhere else, look into catcache.c or elsyscache.c, which is sort of a convenience wrapper over catcache, to see if thing that you are looking for, like I've given some examples, but there are like bunch of things that they are there to see what you are looking for is already there. For inter-process communication, Postgres uses a lot of things, but shared memory segment, shared memory queues, and if you are writing complex extensions, I'm pretty sure you'll probably end up using one or more of these. And I mean, shared memory queue is something Postgres didn't have like till few releases back, but now it's there and it's quite powerful as for a developer. And all of those are implemented under SRC backend storage IPC. That's where you would find most of the code related to inter-process communication. Error handling, yeah, I mean, as a developer, if you are writing new code and you want to handle, sort of exceptions, one is you want to put nice e-report messages where the client can see what happened, what's the error. You also might want to give hints and things like that. So Postgres support all of that, and they are nicely displayed in your console. But if you are looking to handle exceptions at a much lower level in the code, then pgtry, pgcatch blocks these are sort of Java exceptions that Postgres implements using some funky C-level APIs. Like I said in the configure sort of command. Enable C assert is an important thing, and even if you are writing a new code, I would encourage you to think about assertions that you want to put in the code, which you know that should always hold. Tools, yeah, I mean, I'm not gonna again talk about which editors, because everyone would have their own preference. I have gray hair, so I'm an old school boy. So I'm using Vim and CTAG, CScope, and it works wonderfully for me. I have the plugins that I need to browse through the code quickly. I know how to jump from say function invocations, how to find all the variables with the name, and I like everything in my editor. And a lot of my friends now tell me that maybe I should look at something like Cursor AI, who's probably much more powerful. And I'm not gonna say Emacs. I use Emacs for a couple of years after graduating, but last 20 years now I'm hooked to Vim, CTAG, CScope. You can find your own nice spot. So I think we are running out of time, but yeah, so if you want to do a debugging, you want to start with PG backend PID, which will give you the PID, the process that you are currently connected to, and then you can attach to that process to see what's going on and sort of see the code flow. And if you just start a process, if you just start a new connection, get its PID and connect, sort of attach to that PID, this is what the typical stack trace would look like. And I wanted to show this slide because it shows you how the process sort of starts. So you have like the postmaster at the bottom, which forks a new process, which then the backend main is the first entry point for a new backend. It can be a user backend, it can be a background worker process. All of these things would go via this. But then, depending on what you are doing, you will either see that in this case, the backend process is waiting for client to send some data. So it's waiting for some event to happen. And once it gets, some query, it will start the further processing. These are some of the useful guts, like as a developer you want to sort of, play with. You might want to, like log min messages is very basic, but if you look at the other things like debug print plan or debug pretty plan or trace logs or trace user logs, these things are not like very well advertised if you look for other resources. But as a developer, I often find them very useful when I'm looking into some issue with, say, a deadlock that is caused by my code, and I want to know what's happening, or my process is stuck in LW log acquire and I don't know which other process is actually holding that log right now. So if you turn on some of these logs, and most of this code is enabled only when you have assertions enabled, so that's the first thing that you need to do. But after that you can turn on these guts and then you can get much more additional information. Yeah, this is probably not readable, but what I wanted to show is the source code is full of comments, nicely organized things. It will tell you exactly why certain things are done in a certain way. Obviously you are free to improve all the time, but I find the source code very elaborate for my needs. And I just give a couple of examples here, like how elaborate the code commentary can be just at the start of the file, and then there are a lot more. Built-in contrib modules is also a great resource, and I have found it very useful whenever I want to build something new. And each of these, like I just gave some example, like if you want to know how the shared preload library thing works, then PG stat statements, auto explain is a good starting point, because it will tell you if I need to have my own shared memory that I want to manage, if I want my LW logs that I need to use to guard my shared memory, then those contrib modules can give you a good starting point. Or PG prevorm will give you a good starting point if you want to have a contrib module that needs to fork background worker processes and do some extra work that way. So yeah, I mean, test decoding is good starting point. If you want, logical replication is hot these days, and if you want to see how logical replication can be sort of implemented, or output plugin can be implemented, test decoding is a great place to start. and then the source code is full of readmes. I mean, I have just probably listed, I don't know, 20% of them, but yeah, for everything, at least the critical parts in the source code, you will find a readme in Postgres source base. That's it actually. Yeah. Thank you. Yeah.
Like if somebody is new to the Postgres source code in the first place, like especially the core part. So how to go about, you had mentioned about the various, but is there any particular sequence we need to?
I would say, it depends on what you want to do. Like typically if you are looking to, I would say start with the contrib modules. They are great place because they are outside of the main sort of core system, yet they would provide you enough information about how to use Postgres APIs to do certain things internally, or write some simple. I mean, there are some built-in contrib modules which are very simple in nature, yet very powerful, and they will basically. I think that's a good starting point to start looking at. Cool.
Have you done any core development with Postgres in terms of extending any functionality, like which you can just share,
I don't know. I'll have to think about that. But I mean, I've been hacking Postgres. This is my year 19 now. So I think for me, a lot of things now come naturally, and I've probably seen pretty much everything of this. But early days, it was obviously a struggle because these days you find a lot more resources. But yeah, I mean, my favorite approach is still to look into source code and start from there, anywhere else.